So thank you very much. Thank you for being here again. I will start recalling rapidly what I explained the first time, and then I will pass to the theme of the second mini course, the second session of this mini course, sorry. So I explained that the motivation of my work with Angelica Cueto and Dmitry Stepanov, who are here, was a conjecture by Neumann and Wahl, which they call the Milnor fiber conjecture, which predicts that the Milnor fibers of splice-type singularities, which I did not define till now, can be decomposed into Milnor fibers of simpler such singularities. And the decomposition is done in a special four-dimensional way, in four-dimensional differential topology, by cutting four manifold along a properly embedded surface. One does this twice, and then one combines this using a central piece, which is a Cartesian product of the two surfaces. And this was they called the splicing operation. So this was our motivation. Therefore, we had in mind the problem of cutting Milnor fibers into simpler pieces. And as I told you, these singularities are defined using precise equations. So we have at the entrance equations, and at the end we have to put our hands on such decompositions or the Milnor fibers. So I announced that I will treat several points in this order. And last time I covered the first three themes here. I started recalling the prototypical decomposition introduced by Mumford at the beginning of the 60s, the plumbing decomposition of the link of a complex normal surface singularity. That is a three-manifold which gets decomposed using two-dimensional tori. And this allowed me to show that in this game appear naturally circles and tori, which are Cartesian products of circles. Then I showed an analogous decomposition of Milnor fibers. What is common in both of them is that the game is one wants to understand a smooth object. In order to do this, one degenerates it to a normal crossings divisor in a smooth manifold. And the decomposition into pieces come from the irreducible components of that divisor. Then I said that one of the drawbacks of the classical approach started by Mumford was that one has to make many choices of functions defining tubular neighborhoods in order to get either representatives of links or representatives of Milnor fibers inside balls. The choices of balls depend on coordinates. Those coordinates are non-canonical, etc., etc. And then I said that logarithmic geometry comes then as a relief from this viewpoint, is that it brings a doses of canonicity. The doses of canonicity once one fixed a normal crossings resolution. And also it separates the problem of building a representative of either the link or the Milnor fiber into two steps. One, construct a log structure. Second, apply rounding to that log structure. And I finished my first mini course by showing log structures from far away. So I did not show definitions, but I showed what properties are interesting for us. And now I will go to that point and I will show you again those properties, and then enter in the second part where you will have a first glimpse of splice-type singularities, and then I will pass to local tropicalization. You will understand, I hope, why. So these were extracts from Mumford's paper, which I commented on. Here were some very nice representations of plumbed four manifolds and plumbed boundaries of 4 manifolds. Here were the drawings of Milnor fibers and Milnor fibrations one finds in Milnor's book. I recall that there are 2 Milnor fibrations. This was the oldest known drawing of Milnor, of a Milnor tube, in a letter he wrote to John Nash in 1966. Then here I represented the way to see a decomposition of Milnor fibers coming from a normal crossings divisor in the case of germs of functions of 2 variables. These are drawings extracted from the book of Briscorn and Knurrer. This is an intrinsic view of the Milnor fibers decomposed in this way. Then I showed an extract from Grothendieck where he complains about the lack of canonicity. Then I recalled that Riemann's intuition of cutting a surface along curves was an intuition of something which is canonical. And then that Norbert Acampo in 1975 introduced a canonical way to cut a complex manifold along a normal crossings divisor using what he called the real-oriented blow-up. And this was an operation which needed to have a simple normal crossing divisor, because at some moment one does fibered products of operations done on smooth manifolds. And I showed the simplest example of this, in which one gets the analog of removal of a tubular neighborhood of the center of a disk by replacing the center of the disk by a circle whose points represent the real oriented lines through the origin. So each point here, this point represents this oriented line, and the opposite point here represents the same line oriented in an opposite way. And I said that the relation with the usual blow-up is that the points in the usual blow-up on the red circle here represent lines, unoriented lines. Therefore, one passes from the real oriented blow-up to this one by identifying antipodal points. The topology is not the same. Here we have an annulus, and here we have a Möbius band. So this shows clearly that it's not at all the same thing. Then, if one does Riemann's thing, say we have 2 curves intersecting transversally in a surface, and one cuts the surface along this, one obtains, you see intuitively, you understand that you get 4 pieces of paper with corners here. And what is important to notice here is that you get the same result if you remove a tubular neighborhood of the union of these 2 lines. And this is the effect of the real-oriented blow-up of Acampo. This is what he states here at the end of his paragraph. The manifold N, the boundary of his real-oriented blow-up, is homeomorphic to the boundary of every regular neighborhood of x0 in X. x0 is a normal crossings divisor here. And rho is a retraction. So this statement shows that we have a canonical thing, and that canonical thing has the same effect as removing any regular neighborhood. So in this sense, we got some canonicness where it was lacking. Then I said that one can obtain also canonicness, but in a more general setting, which I hope to make you understand, using the notion of log structure and its rounding. And the proposition we have to incorporate here, the message, is that if you have a divisor with normal crossings in a complex manifold, then first, what are the steps of the construction? First, the divisor induces a log structure on the ambient manifold. Then, log structures can be restricted to submanifolds. More generally, they can be pulled back by morphisms. When we restrict to the divisor, then what we have is something intrinsic of the divisor which can be rounded. And the effect of that rounding is the boundary of the rounding on the ambient space. So the rounding of the induced log structure on M is homeomorphic to the real oriented blow-up of M along D. And what are advantages of rounding is more algebraic flexibility. First of all, factoriality. Second, that rounding produces the desired topology. This is this statement we have here, but we will see that this proposition holds much more generally for things which are not normal crossings divisor. And finally, as I told you, if you are interested only in the boundary of the tubular neighborhood, then you can avoid completely rounding by saying the boundary is encoded by the restriction of the divisorial log structure induced by D, restriction to D. So there is this strange thing. On D, one can put a kind of structure which remembers completely the boundaries of tubular neighborhoods. And this is what I will try to make you see. It's not at all obvious, because log geometry is something which, from the logical viewpoint, is perfectly rounded. The definitions are extremely precise, but in general, when definitions are very precise, intuition has problems to grasp what's happening. So this is a pedagogical problem here. That's why I don't want to show you the definitions, because either you already understood in some way and then you learn nothing, or you did not know before and you will learn nothing from the definitions. It's a big problem. So let we see again the main properties we need here for these topological problems. First of all, a log space will be for us a complex space with a structure which is defined in terms of sheaves on it. So there are sheaves. Second, if we have a divisor, any kind of divisor, so complex hypersurface in a complex variety, it induces a log structure on the ambient variety. So this is something which gives you canonically a log structure. And my way to tell you that a complex variety has to be thought as enriched with a log structure follows a convention of Mark-Gross, is to put a dagger X exponent. Here, this log structure is determined by D. So to be precise, I should put in the notation D. And sometimes it's important when we vary, because there is a game of playing with many divisors at the same time. But here I told you that I show from far away. So here the dagger is only to say, now I have an object of the log category. This is a use of daggers here. So now, I told you that a divisor induces a log structure. Now let us see how divisors induce logomorphisms. So now we start from a morphism between complex spaces, which is F here, and we assume we have divisors both on the source and the target. Then we have induced log spaces, V dagger, W dagger. When F induces a logomorphism, when we know that the pre-image of the divisor on the target is contained in the divisor on the source, which means that you can, when you want to study such a morphism logarithmically, you are obliged to take the pre-image of the divisor in the target, but you are not obliged to remain with it. You can enlarge it to put anything else you need for doing something. And this is important, so this inclusion here, which is not an equality, has to be thought as the freedom for work. We have to think exactly what we want to do with those divisors. Fourth, another way to get a logomorphism is to start from a morphism as above, from V to W, but now assume that we have a log structure on W, any kind of log structure, not necessarily coming from this construction. Then one can pull it back to V. Again, I don't say how, but you have to know that this is allowable and it's canonical, and this gives again a log morphism of log spaces. And these morphisms are important because they have special properties, and that's why they received a name. They are called strict. And for us, those which will be important are exactly those which I described. We start from a divisor. We look at the map of inclusion from the divisor in the ambient variety, we take the log structure in the ambient variety defined by the divisor and we pull it back. And the corresponding morphism is a strict morphism. 5. Now we arrive at roundings. Each time you have morphism of log spaces, here V and W denote log spaces. So you see this is a problem. Sometimes a letter denotes a complex space, sometimes a topological space, sometimes a logarithmic space. It's a problem in all the literature. It depends on what is given. Here, V and W are log spaces, and phi is a morphism of log space. When you have something like this, there is a way to construct a map in the topological category, which is called rounding of these log spaces. And it is functorial. And moreover, this new topological space projects canonically to the starting space. And here I emphasize with absolute values to the underlying topological space. Why it is important to emphasize? Because a priori there is no compatibility with a complex structure. This new space is not a complex manifold. As if you remember, when we have a normal crossings divisor, it produces a real-oriented blow-up, which is something with real boundary. So that is not a complex manifold. So you see we arrive at objects of mixed nature, which combine different geometrical categories. So this, that's why when one wants to emphasize this, the notation with absolute values is useful. So below I say that what will interest us is to apply this yoga to normal crossings divisors D in complex manifolds. And in particular, even if D is not a simple normal crossings divisor, rounding the corresponding divisorial log structure has the same effect as removing a tubular neighborhood of the divisor. So now there is a compatibility between the functor of rounding and the rounding morphisms. That if we have a morphism of log spaces, which is phi here, with corresponding continuous map between topological spaces, there is a corresponding rounding map, and here the rounding morphisms, and all of them are compatible, which means that this diagram is commutative. And moreover, this diagram is a pullback diagram whenever the morphism is strict. So in particular, when we start from a divisor with normal crossings in a complex manifold, and first, we look at the restriction of the log structure induced by D on W, the restriction to D, which we call D dagger. We round it. This is the object which interests us. This object appears here in the corresponding diagram. This being a pullback diagram, it means that in order to understand it, we have to look at what happens here and restrict to D. So if we know that the rounding of W is the same as real-oriented blow-up, this means that precisely above D, we have the boundaries of tubular neighborhoods. So that's why D dagger rounded is the boundary of tubular neighborhoods, which means that the boundaries of tubular neighborhoods is encoded in this logarithmic space. And this is a moral for us. If we are interested now in showing that some boundaries of tubular neighborhoods of some Milnor fibrations have inside them pieces which are isomorphic, if we see them logarithmically, it is enough to look at the log variety which gives birth to those pieces and to prove an isomorphism of log spaces. And if we have constructions which are natural enough, we have God-given morphisms between the corresponding varieties, and in those morphisms we will have induced morphisms of log structures, and there we can prove, if we are lucky, that those are isomorphisms. And each time we have isomorphisms, then we get correspondences of parts of Milnor fibers which are isomorphic. So this is the moral. And if I give this mini course, it's in order to show you this. Now, to have an idea, if sometimes you ask, I have two different singular spaces, why inside one I find a piece isomorphic to a piece of the other one, topological piece, meaning that I look at links or Milnor fibers, this is a technique for doing this fact. And the last sentence here, that the boundary of the tubular neighborhood is encoded in D dagger, is an important message of this mini course. Yes?
Just to understand, when you spoke about the real blow-up, then you needed some choice of coordinates, right?
Not at all.
Not at all?
No, no, absolutely no.
Why did you say, but this map, the rounding is canonical?
Yeah, and the real-oriented blow-up also.
Yes, and you say it is homeomorphism locally to the real blow-up. It is the word homeomorphism.
I say homeomorphic because what I said we get by real-oriented blow-ups or by rounding manifolds with boundary. And there, if I would say smooth, the usual way to define smooth is for smooth manifolds. But now there are very interesting texts of Dominic Joyce and his students about smooth structures on manifolds with corners. And I just saw, preparing this mini course, that last year appeared a book on this, with foundations for smooth structures on manifold with corners, which seem very adapted to this. So in fact, there one could speak about much more than homeomorphism, but then one has to delve into those foundations. At some moment, enough people will have understood, and it will be like the notion of atlas of a manifold. In 1930, it was a very complicated notion. Élie Cartan said that, I know what is a manifold, but if you ask me to define, I don't know. So at some moment, all of this will be well digested. But for the moment, I haven't digested that book, which I discovered last week. So I have to practice. But in any case, one can replace homeomorphism by diffeomorphism, but one needs yoga for that. So let's see now how we apply this first to links and then to Milnor fibers. So links. Start from a representative of an isolated complex singularity of any dimension. Now choose a normal crossing resolution of it. X tilde and E is the exceptional divisor here. Now we are in a smooth manifold and we have a normal crossing divisor, so E induces a divisorial log structure on X tilde, which I denote X tilde dagger. That log structure can be restricted to the exceptional divisor. We get E dagger. So I will call this the log exceptional divisor. And now we may round that restriction. So we have E dagger rounded with its canonical projection to E. So this is a representative of the link, and using the projection, it is canonically decomposed in two pieces. Canonically, once the resolution is fixed, different resolutions lead to different representatives with different decompositions, which have maps among them, but those maps collapse parts of them. So we have the same manifold and we have a tower of morphisms between the same abstract manifold, but each time there is a kind of phenomenon of blow up if we go from below to above, or contraction from above to below. So you can say that inside my three manifold I find regions where the phenomena concentrate. It means that I have to climb into the towers. In the same way that we blow up till something where we did not have only normal crossings divisor is shown to our conscience. So now if we do the same game starting from a function f, we start from a Milnor tube representative of what? A smoothing. What means smoothing? In Milnor's prototype, we had a function defined on Cn, so on a smooth space. And I explained that there the nearby levels of a singular level are smooth. So we say that we have a one-parameter family of varieties in which there is a special fiber which is singular and the nearby ones are smooth. This is a smoothing. So in general, we start from something like this on an ambient space which can be singular. And here again, we want F to have the property of being a smoothing, which means that the singular locus of the ambient space should be included in the special fiber, which I denote Z of F. Z of F is F minus 1 of 0. It's a zero locus of F. So we start from such a representative. Again, we take a normal crossings resolution of F, which means that if we compose F and pi, and we look at the zero locus in x tilde, now this is a normal crossings divisor. And again, we play the logarithmic game, but now we have to play it for this composition. So we have the origin in D, so we take the divisorial log structure associated to it. Topologically, it has the effect you saw in the drawing of replacing the point by a circle and creating a cylinder. And here we take the divisorial log structure on x tilde defined by z of f composed with pi. And we get an induced map here. And now we can restrict this to the two divisors. And getting precisely a log structure on the special fiber here, which is a normal crossings variety, and over 0 logarithmic. And this is what I call the log special fiber. So you see, it seems if you did not have a dagger, this would be the abstract variety with a map to a point. And in fact, here it's not the point of topologists, it's a point of algebraic geometer, which is called the spec of C, which means that on this point we can evaluate complex valued functions. So the corresponding field is a C. But here it's that point with a logarithmic structure, whose rounding creates a circle. So now we apply the rounding operation to this, and you see that we get a topological space with a map to a circle. So here the passage from the underlying topological space of this to this is exactly the passage from the point to the circle. And as I explained, this is the reason I chose to denote roundings by this symbol, a point in a circle. And this is a representative of the Milnor fibration. So you see how, again, it is encoded, in fact, in this object, which is a logarithmic morphism. So the first time I saw these things, I understood nothing, but I had the motivation. I knew that I wanted to cut Milnor fibers. So that was my fuel to begin to understand what these things are. And I try to lead you on that path too. So here, this log representative of the Milnor fibration is canonically decomposed in two pieces because of this canonical diagram. We have projections here. So this is a circle projected to a point. So this map is not interesting topologically, but this one decomposes the total space of the Milnor fibration on using the irreducible components of this total transform. And then the Milnor fibers are the fibers here. And now you can therefore intersect the fibers here with the pieces of this projection. So this is a diagram in which you see decompositions of Milnor fibers using the divisor. So finally, let me give you a first glimpse of splice-type singularities. Splice-type singularities are generalizations of Pham-Briscorn surface singularities or Pham-Briscorn complete intersection surface singularities. The simplest ones are those which need one equation in 3 variables, and the equations are written here. Here we have to impose something I did not write, but I say orally that the exponents alpha, beta, and gamma should be pairwise coprime. And the corresponding diagram is here. So you see it's a tripod with a central vertex, and on the three edges emanating from it, and near the central vertex, we have the exponents alpha, beta, gamma, which are written. And the variables x1, x2, x3 label the leaves here of this tripod. And this is how we know that alpha corresponds to x1. And here the rule to pass from the diagram to the equation is very simple. You look at the variable of a leaf, you look at the edge arriving there, you look at the weight of the edge, and you put it as an exponent. And then you make a sum. And in fact, it's not important to make a sum. Here you can put any coefficients, provided they are non-zero. So those monomials are compulsory. Things become stranger when you look at more complicated diagrams. So this is an example. This is a tree, and we have two internal vertices. What is common is that, again, variables correspond to the leaves. So here we have 4 leaves, which correspond to the variables x1, x2, x3, x4. And now we have 2 equations, each equation corresponding to a node. So the first equation here corresponds to the left node. You see that here we have edges which arrive directly to edges. So there the rule is as before. Here we go to x1, the weight is 2, so we say we have the monomial x1 squared. Here we go to x2 with weight 3, x2 cubed. But you see that in this direction where we go to another node, so we do not arrive directly at a leaf, we do not have a power of a variable. We have a monomial in the leaves we see in this direction. You have to imagine that this is your universe, here this is your planet, and you look at stars in this direction. The stars are the leaves. So here you see the stars x3 and x4, and you have to find a clever monomial in those stars. And here it seems x3, x4, but you see that from the viewpoint of this second node, if you look in this direction, you see the monomials x1, x2, and here the exponents are 1 and 4. So what are they? I will explain this later. For the moment, I want to show you that this class of singularities is determined by trees, which have numbers of them, and there is a game of transforming a combinatorial object in a system of equations. And then what interests us is to understand the Milnor fibers of such objects. So such objects, in fact, by the rules of the game, are always isolated complete intersection singularities. This has an implication for the problem of understanding Milnor fibers. I told you that to define a Milnor fiber, we need to have a smoothing of the singularity. So a one-parameter deformation with smooth nearby fibers. In general, the topological type of the Milnor fiber depends on the smoothing. This is, for instance, what happens. This phenomenon occurs already for singularities of toric surfaces. There are a lot of different Milnor fibers with a very interesting topology. And this is something which was a patient for me in the years 2000. I make a work with Andras Dmitry on that. But here, each time you have an isolated complete intersection singularity, Milnor fiber is independent of the smoothings. So that's why we can speak of the Milnor fiber. And this again brings us a degree of freedom. It means that we are completely free of choosing the equations of the smoothing, such that we will work pleasantly with them. So we have to have this in mind. If we change the smoothing, what will change is the monodromy of the smoothing. But the conjecture is not about monodromy, it's only about the Milnor fiber, and that does not change. So that's why we have this degree of freedom of choosing the one-parameter family. And so here you understand that what is given is a precise system of equations. Part of the problem will be to deform it in a way which remains analyzable. simply to show that it was possible. So thank you for the question. Again, here what is important, you can put any coefficients. And you can also add terms of higher weight with respect to canonical weights. In fact, the part of the game is that each node determines a weight vector. And if you add terms of higher weight, it will define singularities which lead to the same Milnor fibers. So we have a great degree of freedom in putting monomials depending on what we want to do in our computations. And also, you could also put complex numbers here. Again, what is important is that these monomials be there. So first, what I want to explain you is the reason of the name. Splicing two objects is taking objects of the same type and combining them into one object of the same type. And if you go on Wikipedia, you will see that you have splicing of many different kinds of objects. For instance, of ropes in the first example, and you have various kinds of splicing. Here you have long splice, the splice used to join two rope ends forming one rope, the length of the total of the two ropes, etc. Short splice, and this is an example of short splice. And you can also have splice joints of pieces of wood in a construction. And if you want to explore, you will see that there are many other examples of technical splicings. So here the idea was that this tree can be obtained by splicing two tripods, the tripod here and the tripod here, and they are spliced along this edge. So this is the reason of the use of the term splicing in this context. So now, what I showed you is that we work with singularities defined by concrete equations. And I told you that we can study Milnor fibers and decompose them into pieces using fundamentally normal crossings resolutions. So we want to pass from equations to explicit normal crossings resolutions whose structure can be read on the equations. So here, this is a problem. Well, for this problem, then we arrive at the question how to construct normal crossings resolutions starting from these equations. In the setting, I told you, the total space is not any more smooth, is any singular germ. And again, what I write in this paragraph is what I told orally before, that when we have isolated complete intersections, we can choose any smoothing for getting a hand on their Milnor fibers. So in order to answer to this question, how to get from equations to resolutions, I will take again the Drosophila of singularity theory, cusp singularity on which you can illustrate all singularity theory. And here I will show you a basic thing you all saw once, but I will comment it in a way which is adapted to our purpose. So here I start from a polynomial of degree 3 in two variables, so which defines a global cubic in the plane, but which has a cusp singularity at the origin, as can be seen from these two terms here, y squared minus 2x cubed. I put minus 2 in order to show that it is possible to put another coefficient, not to be obsessed with a standard form y2 minus x cubed. So, this is a representative of the curve near the origin. And here I drew also the two axes of coordinates. Z of x is a y-axis on which x varies, and z of y is the x-axis. The origin is called P0, so it is the first point to be blown up. So we blow up the origin, and we introduce E0, a first exceptional divisor. In this way, the two axes get separated here. And if you want to follow them in the process, you can follow the colors. Now here, the strict transform of the curve, which is by definition taking the part of the curve outside the point, lifting it here and closing it. This new curve, y1, is now smooth, but it is tangent to the exceptional divisor. So, for this reason, we still don't have a normal crossings divisor. So we have to blow up again. When we blow up, now we get a curve which is smooth and transversal to each component of the exceptional divisor. But the total transform, which is a union of the exceptional divisor and the strict transform, is not a normal crossings divisor. That's why we have to blow up again this point. And now if we look at the total transform, we see that it's a normal crossings divisor. And here I did something which is important for us. Remember that we work with concrete equations, and when working with concrete equations, it's important not to draw only the zero locus of f, but also the axis of coordinates, or the hyperplanes of coordinates. That's why I also draw the strict transforms of the axis of coordinates, till the end. And also with them drawn, you see that you have a normal crossings divisor, which means that the total transform of the curve defined by x, y, f is a normal crossings divisor. So this was a horizontal line above. But if you say that what you are interested in is that to get an abstract resolution, so a smooth curve, and that the smooth curve be transversal to the exceptional divisor, you see that this is something you check in the neighborhood of this point. And what happens in the other parts of the manifold here is not important. That's why the two divisors created by the first two blow-ups, which are E0 and E1, I write here E0, 3 to remember that we look at them on the third level of the blow-up. These two, you may contract them to points, getting these 2 points here. When you contract them, you get a singular surface here. But it turns out that this singular surface shares with the other ones here a nice property. It is a toric surface. And what is a sign that all of this can be described by toric geometry is that if you look at the two axes of coordinates, at each moment we blew up only points which are intersection points of the previous divisors. So here the intersection points of these two, here of these two, here of these two, till we arrive here. And then we contract part of the divisor we have. All these operations, which we describe for the moment geometrically, are describable torically. In which way we would get out of the toric world if now this point P3 I decided to blow it again. This would not be a point of intersection of components of the previous toric divisor. Because here I get something which looks normal crossings, but with a strict transform of the curve, not of the only axis of coordinates here. So if I do this supplementary blow up, I get out of the toric universe. So that's why we stop here. So you see that from the viewpoint of getting a normal crossing resolutions in the toric world, it is enough, in fact, to get this. And this can be obtained here by one toric blow-up. Why one? Because you see the usual blow-up replaces the point by one curve. And this map also, you create only this one curve. It turns out that this toric morphism is in fact a weighted blow-up. And therefore there is a weighted blow-up which is in fact attached to this curve. And the question is why my cusp asks me to perform the weighted blow-up and not to be an obsessive person of blow-ups of points. Making blow-ups of points is something which we can always do and which makes us not to look at the intimate nature of our object. Here the game is first look carefully at our singular object, and the singular object tells me, I have some preferred weighted blow-ups to do. Let's do them. So let's look again at the previous diagram of morphisms from the viewpoint of toric geometry. We started from C2. The toric encoding of C2 is a standard quadrant in the plane, like this. What's the meaning of this? We have to imagine, in fact, only the integral points inside this quadrant. Say, if you have an integral point A, B, you have to put A and B as exponents of a variable t, and to imagine the parametrized curve t to the A, t to the B. This will be a curve, special curve passing through the origin here. And now we are looking, t to the A, t to the B, a priori A and B are integers. And we look what happens when t converges to 0. So for instance, t to power minus 1, t to the power 1. This corresponds to taking a point here, so outside the quadrant. Because of t to the power minus 1, when t goes to 0, you escape to infinity. So you do not have a limit when t goes to 0 inside C2. But if you are here in the quadrant, it means that both exponents are positive. So when t goes to 0, you get a limit in C2. So a meaning of this quadrant is that it shows which monomial curves t go to ta, tb have a limit in your plane when t goes to 0. And this is the meaning of all these pictures. Here, in fact, if you see that you have a divisor and two curves, you see locally two pictures of this kind. That's why you see two two-dimensional cones. And what we are looking at is for each such curve, now we look at the strict transform in this new surface, and we ask the same question: what happens when t goes to 0? And instead of just asking, does the limit exist? The answer will be the same. It's a total cone here. We ask, what is the limit? And it turns out that there is a finite number of possibilities. There is one possibility if we are on this ray, one in the interior of this cone, one on this ray, one in this cone, and one here. And that's why you understand why here we have a partition. Because we partition, in fact, the space of monomial curves according to the limit when t goes to 0. And this is the meaning of a fan. That's why fans encode toric varieties, because you have a toric variety, which means what? We started from C2 here. And we have to imagine that this C2 is C star square, so the complement of the two axes, that we do not touch. That is the starting universe. Both coordinates non-zero. And then the two axes are at infinity from the viewpoint of the universe. And each time we have something non-compact, there is a big desire we learned from the 19th century to compactify it. Because otherwise we have things which escape and we don't know where. And a lot of mythology was created thinking that the universe was not compact. And in the ancient times, that's why one had a compact model of the universe with the stars on a sphere and nothing behind. What was behind? Nothing. Why? Because if something was behind, it was again non-compact. So ancients felt the need to work in compact universes. But the problem here is that there is no canonical compactification. So there are a lot of ways to put things at infinity. And here, all the fans describe precise ways of putting things at infinity, which from the algebraic viewpoint are very easy to describe, because one passes from one to the other simply by monomial changes of coordinates. And that's why here monomials are important. So the game is that all this, what you see here, is a rule to describe what we put at infinity and to compare two ways of putting things at infinity. So very well. So let's see now what's this process. I said that first we blow up the point. when we blow up the origin of C2 from the toric viewpoint, the rule is that we take the primitive generators of the two rays here, and we make their sum. We get this point. And now we take the ray generated by it. That's the blow up. Then I said that we blow up again a point. Which point? A point which corresponds to P1, to this cone here. So again, we make the sum of these two, we get this point here. And then we arrive in this cone, we make the sum of these two, we arrive here, and we get this ray. And when we make this contraction of the two components, it means that we decide that these two rays here are not needed for our problem, and we keep only the last red ray, which is this one. So finally here, from the viewpoint of getting a resolution, what is important is only this ray. And let's keep this. So we have the left diagonal morphism, which I represent horizontally now, and the corresponding toric encoding. And then the question is, well, how do I extract this ray from this polynomial, the starting polynomial? I think you know this, or at least some of you know. Well, here the answer can be done in terms of the oldest combinatorial object associated to singularities, which wears the name of Newton. Newton, even if he did not introduce the full polygon, he describes the first edge of the polygon. So he said that one takes all the monomials appearing in the polynomial, like here, then one starts from this one takes this vertical rope, your hand is here, and now you move to the right. And you will move till the rope, in fact, will be blocked by a point. So when you turn this like this, at some moment you are blocked here. And this is the first edge. And here it's a full Newton polygon. But in general, what you do is you have all these points which are called the support of F. You translate the quadrant at each one of them, you take the union of the translates, and now you take the convex hull of the union. And in particular, here you can have any finite number of compact edges. And now what is this line in our context? Well, I think that the picture shows it. It's the orthogonal to this edge. So our singularity tells, look at my Newton polygon, and now please do the weighted blow-ups in the directions of the orthogonals to my compact edges. So this is, say, the simplest example of local tropicalization. This red edge here is a local tropicalization of the germ of this curve at the origin. Second way of doing this, I said let us pass through the Newton polygon. Now let us remember how Newton arrived at this Newton polygon. His problem was to compute parametrizations of a curve defined by f. So to find two series, x of t, y of t, such that f of x of t, y of t is 0. And Newton polygons allow to show that if you have such series, and you look at the leading terms, meaning that the coefficients a and b here are non-zero, then the exponents have to have this form, 2k and 3k, meaning that their quotients have to be to give the slope of that half line. So you see that that half line, you can also describe it by looking at the arcs contained in your germ. And if you look at this, you see that it's not important here to have a plane curve singularity. You can turn this into a definition. And for me, this is the simplest way to tell to somebody what is local tropicalization. And this is what we say at the beginning of the introduction of a paper which will appear in the Handbook of Geometry and Topology of Singularities, an introduction to local tropicalization. We start from y, which is a germ in Cn. And we believe that the shortest definition of local tropicalization is the following. We look at the arcs contained in Y, and we look at their leading terms. What we ask, again, is to keep in mind that we are doing toric geometry, so the basic space is a torus. So that's why we are looking at arcs contained in Y and not in the toric boundary. So arcs which enter in the torus, which means here that all these coefficients are non-zero. And therefore, all these exponents are strictly positive. You take the vector formed by these exponents, and now you take the ray generated by that vector. You have a union of rays, so it's countable because it's generated by integer vectors. But now this union, well, when you close it, you can have something uncountable. And this is what happens in general. Definition of local tropicalization, you look at all such arcs, their weight vectors, corresponding rays, union of rays, and you close. This is a definition of local tropicalization, and it generalizes what we saw for plane curve singularities. And what I say here at the end is, in the case of plane curve singularities, what we get then is a union of rays orthogonal to the compact edges of the Newton polygon. Let's take an example in dimension 3, a Pham-Briscorn singularity with equation as written before, x1 alpha plus x2 beta plus x3 gamma equals 0. Then again, it's possible to get the local tropicalization from the Newton polyhedron. Here, the Newton polyhedron has this shape. We have a triangle whose vertices correspond to the three monomials. And then we have also in each plane of coordinates, we have the previous Newton polygons. So the Newton polyhedron here is a non-compact polyhedron with one compact b-dimensional face, its edges, and three non-compact two-dimensional faces. The local tropicalization is obtained as before. We start by looking at the orthogonal ray to this triangle. It is this one who's generated by beta gamma, gamma alpha, alpha beta. And then we have to look at the nearby facets of this compact triangle and take also their normals. Their normals are the axes of coordinates. And each time we have here an adjacency of facets, we have to fill the two rays by the corresponding two-dimensional cone. So here what we get at the right is a union of these three two-dimensional cones in these three colors. This is a local tropicalization in the sense just seen before. And when you see it like this, you see, in particular, a fan. These three two-dimensional cones and their edges, as well as the vertex here, form a fan. And when one sees a fan, one learns that there is a toric morphism associated to it. In fact, a toric birational morphism from C3. And what is important is that the fan of C3 is a full non-negative quadrant here. And you see that this fan, if you take the union of its faces, it does not fill this quadrant. This means that this toric birational morphism is not proper. Being non-proper, what could happen is that we start from our surface singularity, we take its strict transform, and we restrict the morphism to the strict transform. It's possible that this again will not be proper. And if you want a resolution, a basic constraint from resolution is that there are proper maps. Well, the miracle of this is that this object you see on the right, which I call the local tropicalization, gives you a proper map when you restrict to the strict transform of the starting object. And in fact, this is a toric interpretation of local tropicalization, which is the following one. This is the second paragraph in our paper. For the geometrically inclined reader, perhaps the most suggestive viewpoint on local tropicalization is the following toric geometrical one. So we start from y in Cn again. Cn is thought torically, and it's determined by the non-negative quadrant sigma 0. Now we take a fan f whose cones are contained in sigma 0. It determines a canonical birational morphism to Cn. This birational morphism is a modification, that is, it is proper if and only if the support of the fan is equal to sigma 0. But if not, what we are interested in is y, not Cn. So restrict this to the strict transform yf of y. And we ask, when is this restriction proper? Answer, this is proper if and only if the support of the fan contains the local tropicalization. That is, the local tropicalization can be interpreted as the intersections of all the fans which give you proper restrictions to the strict transform. And it turns out that that intersection is itself the support of a fan. So it means that we have preferred modifications of y dictated by the way they lie in the ambient space. So not, for the moment, not the precise equations, but the fact that we have coordinates in the ambient space which come from the local tropicalization. They say we should not begin to blow up in all the senses. First determine the local tropicalization, and then try to determine precise fan decompositions of that local tropicalization. In good cases, that thing leads to resolutions. This is called the Newton non-degenerate situation. And so what I will do tomorrow, I will continue speaking about Newton non-degeneracy. So thank you very much for your attention.
Thank you. So thank you very much. Do you have short questions? Comments? Okay, so I think we'll resume in 5 minutes. So let's thank again.